Hey guys, how's it going? In this little video, I'm going to show you how to I make a rig to keep an object outside of a volume uh, or inside of a volume. It is that flexible. You can choose. So to get right into it, let's show you a little bit this setup. So this sphere, this knob sphere, is representing my volume. In fact, when it comes later to I show you the rig, the sphere is not actually a volume, but it's really just a surface, because we are determining the collision via the comparison of the surface normal and the closest point to the driver point vectors. So I'm going to show you that later. But so yeah, this is in that case not real volume, but we could simulate, we could like fake it to be one, and I'm going to show you later what I mean by that. So let me just show you here. So here's a sphere, no sphere. I'm using the sphere because rather than polygons, this is giving me a much better slide when it comes to the object sliding over the surface. Because this is actually represented by mathematical functions, even though you can see edges here is just the viewport that is tessellating the surface to draw it as a mesh. But under the hood, this is mathematical function and everything is super smooth. So you will notice soon why I mean. This locator is my driver locator, and this is my driven sphere. So this is the sphere that is rigged to be colliding with this surface. So if I show you, I have the attribute here called keep driven, and currently it says keep driven outside. So this means if I move this, it can move freely on the outside of this thing, but as soon as I put it here, you can see it cannot enter. And since it's a local, it's kind of a local type of vector comparison, it works from any angle, so it doesn't really matter where I put it. It will always be outside the volume, and it won't be able to move into the thing. So if I put instead my keep driven inside, you can see now I can move this outside and this object will follow, but just sliding on the surface. And if I move this inside, you can see now my sphere can be only inside and it can't exit this thing. So it's an interesting rig. You can use this for make collisions between some muscle drivers and other volumes like the chest. So if you have like the character arm on the chest, you can have a collision rig like this to drive some volume, some muscle shapes that work there, or different types. In the end, it's up to you to imagine what someone could do with this thing. It's a very important, very interesting, I mean, type rig. So yeah, in the end, you see it's very easy, and even if you apparently things correctly, you know it's a global translatable and scalable, and you can do whatever you want to this, and is working still fine. Also, this you can also move the sphere, you know, scale the sphere locally, rotate it like this. You can also move the sphere vertex points, and it'll work just fine. Even you can even, if I undo this, make it like an actual sphere again. You can even do this on not a like a closed volume. So if I were to open the sweep, now you can see how this mesh is always staying here, and if I go further, it won't be going further. So in the end, this is now a projection because of the closest point on mesh evaluation that we're doing. So in this case, it isn't really that fancy, but it's a good way to have a surface collision where the driver really doesn't need to well, the entire matrices can be rotated however they want. So in this case we would say keep inside, and now it's always inside. So, but let's keep the speed, let's switch to 60, so I have a complete volume, and now this is how it behaves. So let me go to the outline, to the load editor and show you the connections. So I'm not going to rebuild this from scratch because you not learn too good with like step by step. It's much better if I show you this and you try to understand the problems and rebuild them yourself, and then you can see much better what is happening. So let's get to the beginning here. This log is my driver log, my driver locator. So I need the position of this log, this word position. To get the word position, I am using the decompose matrix, so I'm plugging the word matrix of the locator into the decompose matrix and then using the translate, which is okay, but I'm a little deep here. If you use a locator, it's much better to use the word position of the shape of the locator, so this attribute here. Why is this? Because if I freeze this locator, the output of this current rig will be zero, but not the shape. The shape will always be the world point of this point here. So this is and it doesn't matter what's the hierarchy on top of it, if you scale, if you rotate, if you freeze this and that and put back, and it doesn't matter, this will always be the absolute world position of this point. So this is a much more stable solution. But for now, I just leave it like that. Okay, so we get this point, we plug it into a closest point on the surface node with this current sphere. Excuse me, have a little bit of sore throat. Okay, so we have this node sphere, we plug this into the closest point on surface node. So it's very simple. In position and in position, and the node sphere world space into input surface. Okay, from here we can get a parameter u and v. We feed that parameter u and v into the point on surface info, which can give us many things, information of the surface. So but only things we need is the normal on that point and the position of that point. So, and here comes the theory. Let me just show you a little Photoshop. It's here. So imagine this is our sphere and this is our current point. We can draw a vector from, so imagine this is a point and the result closest point on the sphere is like here. So you can draw a vector from here to there. On this point we can also get the normal, the surface normal, which is a normalized vector of the length 1, which pointing outside or inside depending on how your surface direction is going, but normally it's outside when you create this maps here. So from this we can calculate, it doesn't matter where your point is. So if there's like a new point here, then the closest point of the mesh would be here, so you know the vector would be like this, and the normal would go parallel in the opposite direction to that. And now if our point is inside the sphere, so let's say it is here, then its closest point on the sphere would be, let's say, here. So you need to try to imagine this in 3D space, and this is inside. So our vector go from here to there, and our surface normal still going outside is going from here to there. So you can see now our vectors are parallel. Excuse me. Before, when it's outside, our vectors are pointing opposite directions. We can use the comparison of these two vectors to determine if we are inside or outside the sphere. And I'll show you in Maya how it goes. But it is actually a very simple operation using the dot product. So, yeah, the only downtime to this is when our driver point is exactly on the sphere. We draw a vector, or we use a vector of the length 0, because when it is on its closest point, the vector is here, and the closest point is here on the exact same point, and the vector is zero length. So Maya will return you an error if you work with a vector of 0 length. Luckily, in theory, I mean, in practically, this never happens. So you can see, I can try my best, but the only way I can get this to error me from the 0 vector length if I were to hold the C key to snap to the surface. Why is it erroring? Well, anyway, appears to be stable, so doesn't matter. Okay, so disregard the 0 length thing. Apparently it works. So yeah, actually this is the thing, and basically this is just it. So we plug this into a simple condition rig, where if our vectors are parallel or pointing in the same direction, we do one thing, and if they are the opposite direction, we do the other thing. So we can do a simple condition rig. Oh, sorry, conditional rig. So yeah, to do this, we need the vector between this point and that point. How we do this? Well, we subtract the one point from the other. So if I show you here this example, and let's say our world 0 coordinates is here, so this is 0, 0, 0, where this is y, this is I don't know, x, and this is z. So how we can get this vector to this point? Well, vectors are represented in lines from the origin. In this case, it's better if we use this one, because if I draw a line here, it will be like almost overlaying with this line. So let's use this line. Yeah. So this is one vector, and then this is the other vector. So to get this vector here, we need to subtract this vector from this vector. So if we do this, it was like, let me just undo a quick thing, draw this vector on a new layer. So now we can use this and move it to there. And then you can see, if I take this vector and subtract this vector, we get this point. If I do the other way around, let me just show you really quickly. Let's put this back. Oh, perfect. Actually, yeah, we want to do it this way. Sorry, it's not the other way around. In the end, it doesn't matter, because then just the results will be inverse. So it's just a matter of inversing the condition functions. But anyway, so you can subtract this point, actually this point, from this point, and then you get this vector, which is basically the direction pointing from our driver to our how it's called, our collision point. So I'll show you here. It's easy using plus minus average node, using the 3D input port, setting the operation to subtract, And you can see here I'm subtracting the driver point from the surface point. So it's exactly what we did here. This is the surface point, and I'm subtracting the driver point from that to get this vector. So this is the right way. Okay. From there, we can use this vector, plug it into a vector product node with normalized output. In this case, it doesn't really matter. In the end, this normalized output will be important for a later enhancement of the rig. I'll show you soon. So I have this temporary transform node where all of my vectors are going in, and you can see here the rotate is currently connected to the comparison. So you can see we have this vector, which is let me draw just a new thing from here to there. So the blue vector, which is basically equal to this, not just in the origin, but it doesn't matter, we just need it in the origin. So the blue vector is going into scale, and the translate is the normal, the surface normal on that point, which is always pointing outside, perpendicular to the surface. Okay, so then we use these two vectors to perform our dot product operation, and we plug the result into the rotate here. You don't really need this transform. You can, plug it directly into this guy, from there directly into the output, into the condition node, but it doesn't matter. I use this to test things because this was like an experimental thing. Okay, so let me just show you what this behaves like. You have a look at the rotation channel of this, because that's the dot product's result. So let me just do a quick disable auto selected, and now you can see all the values are equally are just the same, because the product outputs a single float value but to all the three channels. So I just plug one to the output into rotate, but it doesn't matter because they are always the exact same. So it doesn't matter which one you keep on working with. But you can have a look at the dot product's mathematical function, and have a look on internet so you can see what it does and have a better understanding of how this works. But anyway, so you can see this operation is always negative. So you can see when I'm outside the surface, it doesn't matter where exactly I put it, left or right from the surface, or up or down, or north or south, it'll always be negative. And as soon as I come into the surface, it's now positive. And it is really not important if I'm close to the low point or to the high point, or here or there, it's always positive, and when I come out, it goes negative. So it's easy. You can imagine from here, if this vector or this attribute is greater than 0, we do the one thing, and if it's lower than 0, we do the other thing. And the one thing and the other thing I show soon in the condition node is to either drive the sphere by the position of our point on curve info, or by the position of our locator driver. So, and here's the thing where I wanted to show you. If we go to the vector product node, I had the normalized output on, so they give me a length of 1 all the time. If I show you then the result, it is 1. It always stays 1, or is negative 1, or sorry, 1 and negative 1. And that's okay. We can use this for drive the condition node. It's just a Boolean thing, so it's a kind of a Boolean thing where it's either one value or the other, and never something else. Apparently this is not, so yeah, actually yeah. And but I figure out, if you want to do some more fancy stuff, you can disable the normalized output. Why? So instead of driving a condition node, you could drive a pair blend node by a remap value node. So you can have like a smooth blend between one position and the other, the closer this object comes to the surface. So if I show you this thing again, you can see the closer we go to the surface, the smaller this value is going to be, and then as soon as we get on the surface, it's going to be 0, and then it switched to -1. So we can drive a remap value or a driven key, it doesn't matter. I prefer using remap value nodes because they have options, you know, over the curve. So you can connect objects into the curve and have some. You can connect all things into the interpolation attributes, and you can do all sorts of fancy stuff with this. And you have not that kind of flexibility with the animation curve node. So this is just a side note on that one. So yeah, so you could have like your object be inside the volume, and as soon as you start to reach the next to the surface, you can smoothly blend to the next position rather than stop. It's a hard stop. And the other thing would be like a very smooth blend, depending on how you connect this and how you rig this remap value to the per blend. So, but we don't need this now. You can do this later. So yeah, we have this now. It's very easy to see what's happening from here. My first term is the result of the dot product operation, and if the first term is operation, so less or equal in this case, we do one thing. Color if true, in this case I plug, let me see, the control position, and then color if false is the point on curved surface info output position, or actually the other way around, but it doesn't matter, because you just need to change the operation type to get them the likely result. So, and the output color you plug into the sphere, and here we can have a thing. So my locator, remember it has attribute, currently driving with a set-driven key. The keep-driven attribute is plugged into the operation. So we can do the different things from here. We can invert the function from here. So this means, I showed you before, when this is set to inside, my operation is less or equal, which means the dot product is less or equal, is smaller than 0. So our mesh is outside, or if we put it outside, now the operation changed to greater or equal, which a pretty simple rig. So now you can see it's not going inside. So that was it. It's a pretty simple setup. You can go much complex from here. For example, you could try to make a rig where you have your driver point and your surface point. You can, from there, you have like this vector. You can then determine a point along this vector on your driven mesh, on the base copy of this mesh, and you can use this point to compare. So then you could have like a true collision, a kind of a true collision, because it would be still a fake collision if I were to scale this sphere. And let's rotate this to like simulate kind of a closest point vector. So you can see now, if we were to do this, we would use this point as a collision point, but would collide to area with this. So you would want to keep an eye on this. But this is like one of the only ways to do this mesh-to-mesh collision with the simple Maya node rig, because otherwise would have to iterate with a certain tolerance through all the points on one surface and compare them to all the points of the other surface. So it would be a very heavy computational process. So doing this with like a fake process of using the center point or the driver point, drawing the line to the closest point on the driver mesh, determining the point along that vector on the base driven mesh, and using that point to do the collision stuff. You can also, you can also align the surface, so the driven object, to the surface very easily, because our point on surface info gives us a lot of results. So we are using the normal, but it is also giving us normalized normal, normalized tangent u, normalized tangent v, tangent u and tangent v, everything we need. So we can, from the normal or the normalized normal, we would rather use the normalized output, can build from these three vectors a matrix, and use this matrix to orient our surface. Let me just quickly show you how to do this. So you would use a 4x4 matrix. So attributes, and now you have here all the inputs. And maybe you want to look on the internet how a matrix of this type of format is set up. So I'll quickly just show you the input 0, input 1, input 2, and input 3. And every of these inputs has 4 plugs. So this is how it goes. The first input is the front axis, the second input is the up axis, and the third input is the secondary axis. And then the fourth input is the position. And the last plugs of each input you leave as they are. They don't matter in this case. Okay, so in this case we want to use, let's say, tangent u as the front axis. So tangent u y, tangent u z, the first one. Then we use the normal, of course, as the up vector. So input 1, input 2, input 3 there. And then we can use the tangent v as the secondary up vector. So plug this 1, 2, 3. And then, of course, from here, the third input, or the fourth in this case, so in 3, 0, in 3, 1, in 3, 2, are determining the position. We don't need this in this case because the position is coming from somewhere else, so we can just leave them empty. Now we have built our matrix. We can use the decompose matrix now to decompose it into 3D transform values that we can use. Put the input matrix in there. And now we would need to use a second condition node to have it either drive the rotation of the object by the driver locator or the output of this decompose matrix. So let's do that quickly. Condition. Let's just quickly recreate the channels here. So first term is object x. Let me just grab the locator. Oh no, we don't need the locator, we need the second key node here. So we plug the output of the strip key node in the operation. Oops, sorry, need to drink a little bit. Much better. Okay, and then the color if true and false is in this case our decompose matrix output and the locator rotation. So which one goes where? Let's just quickly check. So this is the surface is going into the color if true, so the upper matrix needs to go into the color if true, and the locator rotate needs to go to the color if false. Sorry, and the upper color into the rotating. Oh man, I need to finish this soon. So now you can see our sphere is orienting kind of the this shouldn't be happening. Uh, Something is mismatching here. So the rotation channels appear to be the same, but the surface, the sphere is rotating in a different rotation order. It's like a gimbal thing. But the super weird stuff. Ah, I see. Okay. Excuse me. We have a little problem here now because the if I do zero out the global translate group, this works. Now you can see it's orienting to the locator. So if I put it here, you can see now it's orienting to the surface. So this is working correctly. See that? Let me quickly just reshape this sphere so you can see better. You can see now here how the sphere always stays oriented to the surface, always stays pointing upwards. And the cool thing, because of the nice output of the point on surface input, we will never get flipping. Never ever. But the downtime here, again, as I said, some things are not matching up with the local, with the global position, because I have the sphere inside here in order to be able to scale it correctly. But I had the inherent transform of the sphere turned off. If I turn on, sphere goes away. So if I undo this, I need to rescale this thing, and it's still not working. Let's put it back. Oh no, that's not working at all. Okay. So, because of the translate offset. Let's put the translate to 0. Then we can prepare this guy out without any pop. Now it's working. And yeah. So now everything is working. And if we scale this now up, sphere is still following, but the only thing we need to do is plug the scale into the word scale into the sphere scale, into the group scale, if the group is set up to the sphere, you know, that kind of stuff. I think this was it. If there's any questions or comments or critics or stuff like that, post on the comments, and yeah, see me next time. Bye.